Hi, and welcome to the fifth lecture of the control course. Today we're talking about digital control systems. So basically what we did so far is talk about continuous time systems. So everything we introduced in the first four lectures was about continuous time systems. So there was basically no assumption on the resolution of both the controller, so when we can apply the control, or of the sensor, so when we can measure the output of a system or the state of a system. So our assumption was that we can do everything all the time continuously, while in real time what we have to deal with is digital control systems. So we enter the discrete time domain. So as a further motivation, digital systems are discrete time systems, and this is basically what's used in real life, in reality, for control. And especially some advanced control systems such as optimal control and adaptive control is purely digital, and this is something that will turn out to be useful since optimal control is actually, or at least one part of the optimal control is actually a topic for the sixth lecture, where we will introduce some optimal control strategies and model predictive control. Okay, now let's talk about discrete time systems. So what are discrete time systems? What are we talking about and how we characterize them? So the main thing about the discrete time system is that the signal is not continuous, but it's discrete. So the time axis that so far was continuous, so we were having this dense values in the curve with dense values. For example, if you remember the curve of the evolution, where we had this overshoot, transient and steady state, everything was there was no sampling. Now the time is quantized, so it's discrete, and we will have to look at it like in a sort of a grid. So there are some time instance, which is, for example, when the sensor is able to read, or when the actuator is able to give something, which can be small, like this time that we need to wait before one sample and the next one can be very, very small, but it's never zero, it's never continuous. Now, there are two things. One is the time, and one is the values that we can, the thing that we are looking at can have. And the time is quantized, so we can look only at discrete instance of time. But what about the values? Because the values, they could actually be continuous. So there is basically, it could be the case that there's no limitation on the values that our value, the one that we're measuring, can assume. And if that's the case, so the signal can assume a continuous range of values, so we have no grid on the vertical axis, then we have a sample data signal. It's sampled because the time is sampled, so time is quantized, but it's continuous in the values. On the other hand, if the amplitude is also quantized, so we also have to look at the grid on the vertical axis, we talk about digital signal. So there is a difference between digital and sampled, which depends on how many values, like what values can we actually have for the thing that we're measuring. We will have now a visual breakdown of this. So this is the classical continuous time signal. So it's continuous in time and it's continuous in values. So both things are continuous, and this is basically what we've seen so far. So this is basically everything that the first four lectures concerned. Then we have quantization. So time quantization, we can look at the signal only at certain times. And this may be, for example, because of the sensor, because the sensor has to read stuff and can read only every second or every half a second or every millisecond, depends. And so this can be small, can be very, very small, but it's quantized. Then we have a sampled data signal. Sample data signal is something like this. So the time is quantized again, and basically we can look at any kind of value here. So there's no grid on this axis. It's not like there's only certain values that we can actually read or apply, whether it's a sensor or a controller. So it can be anything. The digital signal, on the other hand, looks like something like this. So time is quantized, but also the values are. So the values of this thing that we're measuring, or this thing that we're applying, this signal, generic signal, is also quantized. There are only a certain number of things certain number of values that we can actually have. And this interval can also be very, very small. Imagine, for example, if this is something that can be provided by a signal you have, by a process you have. For example, you have a motor and you're providing something or whatever else. Like this could be small intervals because maybe your system has a very, very, very fine resolution, or it can be bigger signals because maybe it's like some huge system that has like different levels of application. So this is a bit of nomenclature to understand how to go basically from continuous time to digital, passing through the sample data, which is the classic discrete time systems. Now, this is what we said, there's the time sampling. So we have this, for example, in the case of a sensor reads every certain time. Like imagine like you have a camera and you have something coming every like at 30 FPS, for example, you have 30 frames per second coming in, and this is basically the sampling time that you have, right? So the sampling time is typically something periodic. So the thing is, there are also systems that allow you to have sampling time which is not always the same, but it changes over time. But we will not talk about them in this course. For now, we stick with periodic sampling. And from what we've seen before, so from the image that we've seen before, we understood that it's kind of easy to go from continuous to discrete, because it's like you have a continuous curve, you just read at a certain intervals, and if you want to make it digital, you can also just read certain values and you say, I can only see this, and you take the corresponding values. But can you do the opposite? So is it possible then, if you have a discrete time system, to go back to a continuous time system, or to a continuous time representation at least? Well, this is actually possible, and it's possible via the sampling theorem. So the sampling theorem is one of the most important results for digital control systems or discrete time systems in general, and it says that basically it's something that depends on the highest frequency that you have in a system. So if you have a certain system and it's a continuous time system, you discretize it, this system has a certain component, a certain frequency, which is the highest frequency of the system, called the WC, then you can actually go back from a discrete time system to a continuous time system, reconstructing perfectly the behavior of the continuous time system with no distortion, with no loss of information, if you sampled at a high rate. And this high rate is twice this higher frequency. So typically, this 2WC is called Nyquist rate. It's just a name from Nyquist, which is a scientist which introduced the system. And basically, it tells what is the sampling period to reconstruct the system without losing any information, so with no information loss. What is typically done is that the sampling frequency tends to be very, very high. So it tends, like, you try to have a sampling time which is as small as possible. So basically, the thing that you would like to achieve in the end is that to have something which looks at least as close as possible to a continuous time system. So sampling frequency is typically very high for normal systems, because normal systems also like allow to like have a higher frequency which allows sampling this at this rate. And this is like the way to go back from discrete to continuous. Not the way, but a result that you have to keep in mind for going back to from discrete time to the continuous time in order to have a meaningful continuous time system, not something which is an approximation with distortions, with errors, loss of information, so on. So this was just like an introduction to discrete time system, but now we want to look at the actual systems. We have the continuous time system in mind, which is this x dot equal ax plus bu, which we've already seen a lot of times in the previous lectures. How does this translate to discrete time systems? Well, the implicit model of discrete time systems is as close as possible to the one of the continuous time system. So we don't have any more time derivative, because time derivative is defined in the continuous domain, and now we're not in the continuous domain anymore. So we need something else, and this something else is time improvement. So it's like we're looking at the next instant of time as the next sampling time, and we say that the next sampling time depends on where we were before, and an evolution matrix, of course, plus the input that has been applied at that time instant. So it's exactly what you would expect. We don't have any more the variation here, like direct variation given by the time derivative, but we have simply at the next sensor reading, or the next time that I'm able to see what's going on, everything will depend on where I was before and what happened before. This is what we would expect for a discrete time system. So the rhythm has become a time increment, and variables are measured at a time k, where k is this index basically is just going on, and it basically gives the time increment. It gives the time counter for the system. We do not use the variable t, which we've introduced in the last lectures, because t is like commonly used for the continuous time. So when you see t or a system in t, it's very likely to be a continuous time system, where usually discrete time systems have this k, which gives this idea of time intervals rather than one unique time axis on which we can freely move on. So similar to what we did in the very first lecture, when we derived the explicit model by just iterating the implicit model, so we have that x0 is something, and then x1 depends on x0 thanks to this, and then we have that x2 depends on x1, which depends on x0, and so on and so forth. We can do this exact same thing, and we end up with this model here, which is the explicit model for the discrete time system. So again, similarly to the continuous time system, we can split this model, and we have a part which depends only on the state. So when there is no input, where the input is zero, completely zero, this part disappears, and we have that the system evolves in this way depending on which initial state we're in. And then we have a forced evolution, which is the evolution that if the x0 is such as the system does not evolve from it, which we know now this is defined as an equilibrium, so this part disappears, and this would be the forced evolution. So what happens to the system because of the input that is applied to it. So this is what we have, and we can already see that here there are some modifications with respect to what we had in the continuous time system. And this is mostly because now we don't have to solve anymore ordinary differential equation, which introduced the exponential of a matrix, but now we have a matrix which is elevated to a certain power. And this is different from having e to the a t, because now it's just a to the k. So keep this in mind, because this will be actually useful for when we will talk about stability, for example. So apart from this, main difference is that, of course, we don't solve the integral anymore. So we don't solve the ordinary differential equation anymore. So we don't have the integral, but we have a summation. So summation is basically the equivalent of the integral from continuous time to discrete time. And this is what we have here for discrete time systems. So again, another thing that I mentioned already, we have this, which is the exponential of a matrix becomes a matrix to a certain power in discrete time. And this will change a lot, because the free evolution now is governed by this, and it's not described anymore by the eigenvalues, by the power of the eigenvalues, but it's by the exponential of some eigenvalues, but it's described by these eigenvalues elevated to some power. And this is very different, because before we had this e to the a, and this was exponential. And so we had, exactly like the exponential function works, we have that the left half plane was something good, so it was basically the stable part, because the evolution was decaying, because it was less than 1, so it was something decaying to 0. And then when we had eigenvalues were bigger than 0, so on the right hand plane we had something diverging, something that led to instability. In this case we have something different, because this is a number basically elevated to a certain power, and therefore if the number is smaller than 1, when you elevate a certain power, then it goes smaller and smaller, so it converges. So it's basically what we have, what would be the stability for us. On the other hand, if we have something bigger than 1, and you elevate it to some power, this gets bigger and bigger and bigger, also because power is always bigger than 1, because it's the time increment, so it's not something that's less than 1. So this is something diverging. On the other hand, if we have something like 1, then 1 to certain power, it's a persistent evolution that does not neither converge nor diverge. So there is a bit of a difference, and again, visual breakdown for this. Continuous time system, we converge, the evolution converges as long as we are in the left hand plane, and it diverges when the eigenvalues are in the right hand plane. The persistent part is this axis, which is the 0 axis, because e to the power of 0 leads to 1 and doesn't mind if the time goes on, it's still e to the power of 0. On the other hand, for the discrete time system, we have that everything that is inside the unit circle, so the circle with the radius equal to 1, is converging, because we said if we have an eigenvalue here, we have it to a power of 2, 3, 4, 5, which is the time increment. This gets smaller and smaller and smaller, so it's eventually converging. On the other hand, if we have something bigger, it's diverging, because we have a number bigger than 1 to a certain power, it explodes. While if we have 1, or something that is on the unit circle, then this is the persistent evolution. So this is the main difference between continuous and discrete time. And this is quite important to have in mind, because when we pass from continuous to discrete and vice versa, we want to take this into account. We want to, basically what we will see is that we want to map all this area, all this green area, so the converging area, into the unit circle, which is the converging area, and all the diverging area into the diverging area. So that basically, if we have a system, we know that if we passed from continuous time to discrete time, we know that stability in continuous time implies also stability in discrete time, and vice versa. And it's not like, oh, we have stability in discrete time, in the continuous time, sorry, which translates, for example, into stability in discrete time. But then when we go back, this doesn't hold anymore. Because maybe, for example, the converging part gets mapped into the converging part, but only to a portion of it. So there is a portion of the converging part that actually is mapped to the diverging one. But this we will see into more details in a few slides. It's just like to give you a taste of why are these two things important, and you have to keep them in mind when having continuous and discrete time systems. What else did we introduce for continuous time system, which was very useful? Well, we introduced the Laplace transform. The Laplace transform was something that we used to go from the time domain to the frequency domain. Because sometimes, for example, transfer function, the stability analysis, it was very hard to do everything in continuous time because the integrals were hard, because we had this convolution inside the integral, and this was something that was very hard to tackle. And so we passed through the Laplace transform and said, oh, in the Laplace domain, everything is easier because the convolution becomes just a product, and the integral or the derivative becomes just a multiplication by this s variable, or 1 over s, which is this frequency variable. So it was something that was making our life easier to deal with things for continuous time systems. Well, we have the same thing, but of course, if you remember the definition, which you can find on the very first lecture of the Laplace transform, you will remember that is defined as an integral. So the very definition of a function transformed after Laplace is the integral of that function multiplied by stuff. So we cannot have the same thing because we don't have integrals. We are in the discrete time domain now. We cannot use exactly the Laplace transform. So there is another operator which is called Z transform. This Z transform is defined in a very, very similar way to the Laplace transform. There are two main differences. One is that there's no integral, but there's a summation, because again, we are in the discrete time system. We don't have integrals. The discrete equivalent of an integral is summation, because the integral in the end is just a continuous summation over an area of something. And so we have a summation here. The other main difference is if you go back and take the definition of the Laplace transform, the other main difference is that in the Laplace transform, we have e to the power of minus st. So this is something that reminds you of e to the at, which is what comes from the free evolution, from the explicit form of the free evolution. And here, instead of that, we have z to the minus t, which again is something that is very similar to what we have in the Laplace domain. So again, exactly like for Laplace, we have the definition of not derivative anymore, but the time increment. And this is also z multiplied by the transform function, and also of the time delay, which is f over this. So basically, this would be the equivalent of derivation, and so time differentiation and integrals in the discrete time. And we also have all the same, all those properties that we have also for the Laplace transform. So the Z transform is linear, the convolution is basically just a product of it, and then we have the delay doesn't doesn't, yeah, we don't have the derivative, so the time delay is also tackled just with the product by z. So it's all the properties that we've seen also for the Laplace transform, we have them for the z transform. And then what happens when we transform something like this? Well, I can do the computation, but basically this part here is the transformation of the AXK part, while this one is the transformation of the BUK part. This term comes from the fact that we have an xk plus 1 on the left hand side, so there's something coming on this other side, and then we have implicit, like the explicit form of state and output in this way. And again, from this, then we can actually look at this part and we realize, oh, we have actually also here an input-output transfer function. So we have something that gives us the perfect connection, the perfect link between the output, the input that we are applying to the system, and the output that we're reading from it, wherever the output is once we choose it. So this is a transfer function. Now, we introduced a few things. We can put everything together and look at the block scheme of a discrete time system. Of course, it's a bit different from the block scheme of the continuous time systems, because now we have to take into account this discretization, this where does the process gets discretized. One typical way to describe this is something like this. So we have a process, and we assume the process to be continuous time. So the process is just there. It gets an input and it gives an output in return, and everything is continuous time. And then we have something. We have something that is controlling it. It can be like a computer, it can be a motor, it can be whatever you want. But this is discrete because it's not able to have this infinite resolution when applying something or also when reading something. But there's it's discrete. So there are these two modules, because you can see that the reference that is given, since the system is continuous time, the reference is also continuous time, and the output of the system is continuous time, so the error is again in continuous time. So we get this error, continuous time, that has to be fed to a system, our controller, which is discrete time. How do we do it? We do it with something that is called analog to digital converter. So analog means continuous time. So everything that we've seen so far in the first 4 lectures was analog. So analog to digital is something that takes something continuous and makes it something discrete. Then we have this controller, which is a discrete time controller, which takes a discretized version of the error, which of course is not as precise and as rich of information as this one, but hopefully we can sample this error in such a way that, for example, with the sampling theorem we've seen before, so if we do a very, very fine sampling, we don't lose information, and the error which is described here does not alter whatever it's going to happen. Then we compute the error, the controller action. We get this action, which is of course a discrete time signal, because the process that we're using here, the controller, is a discrete time controller. And then we pass it through a digital to analog converter. So it's something that takes a digital signal, sorry. So this digital signal here, and makes it analog, so makes it continuous. So this thing here is one block scheme to make the controller continuous. So we have a discrete time controller and we make it continuous artificially with these two modules. This is something that we are doing with this one. There is another thing that we can do, which is this. This is process, which is a continuous time process, and because continuous time process, so it takes input and output, gets instead sampled. So we have a controller somewhere, which is a discrete time controller that gives a discrete time signal. So we have to convert it to analog in order to pass it to the process. But also we have sensors, and sensors are also like devices, like it can be a camera, it can be a computer measuring something, it can be anything you want, but it's also something that has a finite resolution. It's not something that can read continuously a signal. So the sensor also reads a discrete time. So basically, in this way, instead of making the controller continuous like we did before, we make the process discrete. So the process evolves in a continuous time. It's doing internally things at continuous time, but we need to have a controller that provides a signal which is discrete and then convert it. And then we have a sensor which also takes this input coming from the process and reads it at like as fast as it can, but at a certain sampling time. So it actually gives back directly discretized version of the output. And this clock here is just some sort of alignment, some time synchronization between this sampling and this sampling. So you want the sampling to happen at the same time so that you know that you are applying something at a certain time, and you know that at that time you also see directly how the system is changing. And so you have these two things which are somehow coordinated, so to say. So we have talked about these block schemes a bit, but there are these two parts of the block scheme which we don't really know what they are. So the digital to analog and the analog to digital. So what they are doing, how do they look like, and also like how are they called? So first, digital to analog. This is called holder, and I will show you in a second why it's called holder. But like intuitively, you can understand, like you have a discrete time signal, which is just numbers at certain timestamps, and you just hold them until the next one comes. So this is why it's called holder. And the analog to digital is simply called sampler. So it's something that sample from continuous time to discrete time. So let's go a bit into deep for these two blocks. First, we start with the sampler. So the second one. Sampler is basically a method to sample a continuous time system. So for making a continuous time system actually discrete time, because it's what we need. We said that this is what we need for generating a discrete time system from a continuous time on. What are the ways to do it? How do we do this? Okay, first we have one thing which is called Euler's rule, or forward rectangular's rule, and this is basically we sample at certain times. We just take, okay, we can only see the value of this thing that we're measuring at certain instance of time. So we assume that in the meanwhile, it's not changing. So there's nothing changing. The system basically, if this sampling time is 1 second, means that the system basically not doing anything for 1 second. It reaches the state and it stays there. And it reaches the state and it stays there. And so on and so forth. Of course, when the sampling time is very, very small, this maybe can be accurate. If the sampling time is quite big, you can understand that this is not approximating this curve very well. So this can introduce problems. This is how basically the time derivative in continuous time is approximated for discrete time. And basically this is the Euler's rule for going from continuous to discrete. Now, I will not do the computation in these slides, so they will not be part of the course, but basically this is the transformation that you get with the forward rectangular's rule if you want to go from Laplace to Z. So if you want to go from continuous time to discrete time. So basically why is this important? This is important now because what we are trying to look at is those two pictures that we've seen before of the stability area for the continuous time system and the stability area for the discrete time system, and we want to compare them. And so for us it's very important now to actually compare Laplace to Z and see how are we transforming everything that is Laplace in Z and vice versa. So with this transformation, Z is equal to 1 plus Ts. So basically, this is what happens. This happens because basically S is stable in the left half of the plane, but if we do 1 plus, it actually goes beyond it. So it goes a bit more. It goes to 1 and T is just a rescaling somewhere. So this is the area. So it means that basically if you are stable in S, it doesn't mean that you're stable also in Z, because you can be stable in S and be here and you're not inside the unit circle. So basically this stability is not both ways, but the stability continuous time implies stability discrete time, but if the stability in discrete time implies a stability in continuous time, but if you have something that is stable in continuous time, you are not sure with this rule that it's stable also in discrete time for this reason. Then there is another approach, so another way instead of the forward rectangular rule, which is simply the backward rectangular rule. So we do exactly the same thing, but instead of assuming that the system is not evolving from where it reaches, we assume that the system already jumps to the next value. This is basically what happens. So this is the formulation of how the time derivative becomes into discrete time. And again, no computation here, but this is a transformation between S and Z. So when we invert it and get Z, this is basically like rescaling dimension of the circle. And this is a problem because you can see it here already, like this is where the continuous time gets mapped, and where like the area of stability of continuous time is fine because it falls into the unit circle, but the area of stability of discrete time is not fine because there are some parts here which are not stable for the continuous time. So stability in continuous time implies stability in Z, so in discrete time, but the stability in Z does not imply stability in S. So if your eigenvalues are here, which would be stable in discrete time, then once we go back to the continuous time, this would actually result in an unstable system. And this is suboptimal, this is not what we want. So it's a problem that we need to solve somehow. There is one last thing that we can do, which is the trapezoidal rule. The trapezoidal rule is also known as Tustin's rule, and basically what it does is this linear interpolation between consecutive time instants. So you can see already from the picture that what happens with Tustin, or with this trapezoidal rule, is something very, very close to the curve. And you can imagine that if the time interval here becomes very, very small, this approximates whatever is going on here quite well. And this is some knowledge that should come probably from calculus, where you have that the Taylor expansion, with the Taylor expansion, you have that a linear approximation is a good approximation of a function locally. So if we make this interval, this time interval, very, very small, so we get to a very local neighborhood of this point, then this linear approximation should actually be quite good. And what happens with the Tustin rule is that once this is the transformation that you got from S to Z, this is the mapping. So stability in S and in Z imply the stability in Z and in S respectively. So the mapping is perfect. The whole right half plane, so the unstable part of the continuous time, gets mapped outside of the unit circle, while the left-hand plane gets mapped inside the unit circle, and the zero axis, which is the persistent part, gets mapped onto the circle, so on the edge of the circle. So these are samplers. So these are three different ways to sample. So we've seen this backward and forward rule, which are common. They're easy, especially the Euler rule is quite easy and is quite intuitive, but it might generate some problems. Then, of course, these problems are limited once you have a sampling time which is very, very small, but still they might introduce problems. On the other hand, we have this trapezoidal rule, or Tustin's rule, which actually is better. It approximates better also visually. Once you look at the plot of this evolution that you are discretizing, it clearly looks better. It clearly gives you the impression of, okay, this is a better approximation of what I was doing before, and it actually results in a perfect mapping for stability reasons. So we talked about the samplers a bit. Let's spend a few words on holders. So holders are tools to generate a continuous signal from a discrete one. So again, I told you, imagine that you're holding something. So you have discrete times you're holding until you get the next sign, and then you get a continuous time. You don't get something that is differentiable, because there will be jumps in the function, but you get something that is continuous, which is what we care about. So from discrete to continuous, and this is one way, the simplest way, and actually also the most common way to have the holder. So we hold the signal constant until the next change. Exactly this example that I've already pitched in the previous slides. So basically, for tau, which is smaller than the sampling time, so in the sampling interval, we just hold whatever we had at the beginning of the sampling interval. So this is the input, and we sample it like this. So this is the continuous time signal we get. Again, this is not differentiable because there are jumps here, but it's still a continuous time signal. And this is what we use for this kind of sampling. There is also another strategy, which is called first order hold. This is something that takes into account the variations, and then it tries to also generate something which doesn't have jumps, because jumps could potentially be harmful for example, if you have a controller and you need to apply some sort of input to the system that you're controlling, then having jumps in the input that the controller needs to provide can be a problem, can be like an actual hardware problem then, or it can generate problems to the system. So this is something that would result in something less stressful from an hardware perspective. So this is basically how the increment is calculated, and you can check it's just basically the linear interpolation from start to end, and so you get the variation at each point in time. This is called first order hold because it approximates with a straight line. So zero order hold is just like we take the number, so the point, and hold it. First order hold, we do the line between 2 points. We could go higher, so we could go maybe on a second order hold and have something which is a bit smoother and looks a bit more curvy somehow. But in general, higher order holds are not really common, are not really used. The zero order hold is enough, especially when the sampling time is very, very small, it's fine. Even though it looks quite similar to the Euler's rule on the samplers, it actually doesn't introduce many problems. But also the Euler's rule, as I told you, once you have the sampling time, which is very, very fine, then you actually are able to work with it without any problem. There is not much to say on stability theory because basically everything holds. You just have to take into account that you are changing now the area you have to look at. So if you want to check for stability and you go in your transfer function, you check for the eigenvalues, you can do exactly the same thing that you've done so far for the continuous time system, but you have to check that the eigenvalues are inside the unit circle instead of having negative real part. This is basically the main difference, the main thing that changed, and it's what there's nothing else to add. Also for eigenvalue assignment and all the tests on reachability, it's basically the same thing that we've seen so far. Just have to, if you want to assign an eigenvalue, you have to assign it in the right portion of space, rather than in the left-hand plane. I will just give you one last slide, basically on the Lyapunov criterion, because we introduced this concept of Lyapunov functions. And Lyapunov functions, I told you that is this kind of functions that if they have a certain problem, they ensure asymptotic stability of a system. And Lyapunov stability theorems are basically the main result in the stability theory in control engineering. So there is the equivalent of Lyapunov criterion for stability also for discrete time systems. And if you go slide by slide with what I introduced to you, I think in the second lecture, it's basically the same thing. So we have a system and we have an equilibrium point, and we say that this equilibrium is asymptotically stable if we have a function which is positive definite, exactly as the continuous time function, even if here we're talking about a discrete time function, or at least x is discrete time. And before we had that the time derivative of v has to be less than 0, have to be negative definite. In this case, we don't have the time derivative, but we have the variation of the function. So variation is basically what the value of the function at a certain time instant minus the value of the function at the previous time instant. So we're still looking at some sort of evolution, basically. So this is the equivalent of the gradient that we were looking at in the continuous time case. This also has to be less than 0. So it has to be a downward gradient. So something that basically goes down towards the equilibrium here. And this has to happen in a neighbor of the equilibrium. So Lyapunov criterion for stability also remains completely unchanged in this domain. So we got to the end already. We introduced discrete time systems. I gave you some idea of what is a discrete time system, what is a digital system. We went through modeling, stability. introduced the sampler and the holder, and made, like I showed you a few examples, and how the stability area is mapped from continuous time to discrete time and vice versa. And this is quite a short lecture because it just introduces some concepts that are useful, because the real-time systems are generally discrete time systems. So something you need to know how to go from one to the other, but then most of the things can be just introduced in the continuous time domain and say, okay, it's the same for discrete time systems. So some references here. You can see there are some slides and a book, which is pretty old because digital control system is also like a very, very old topic. And you can check it out if you want more details, if you want, for example, a derivation or how to get to the sampler and holder formulas and things like this. And I will see you on the next lecture, which will be the last lecture of the course on model predictive control and optimal control. Thank you for your attention.